Good afternoon, everyone. We are Team 27. We are the Delivery Robot Project. This is April 26, 2021, and we are a Cal State LA institution. Here, we see the slide of Meet the Team. My name is Jaime Gonzalez. I am the mechanical engineer, the team lead. The team will introduce themselves individually as the PowerPoint presentation continues. As of right now, I'll go ahead and introduce them. To the left here, we have Orville Bahia, electrical engineer. He's in charge of the electrical design components and power analysis. Next, we have Irvin Dolores, electrical engineer. He's in charge of the control operation system for the robot and Gazebo. We have myself, Jaime Gonzalez, mechanical engineer, team lead, focused on design and simulation in ROS. Next, we have Irvin Martinez, electrical engineer. Focus is in sensor application in Gazebo and map server memory. And finally, we have Francisco Tiquiram, electrical engineer, computer vision research using Python and OpenCV. Our senior project advisors were Dr. Charles Liu and Mo Zhang. This is the agenda breakdown for our PowerPoint presentation. It begins with the introduction, which is a basic intro to what our project is and where it comes from. The project structure defines things such as our requirements and the WBS. Our approach is how we approach the project in terms of what we plan to use and some of the components we researched. The design process has to do with the process of our simulation design as well as some of the prototype design, and lastly, the results of it with our conclusion. Last mile delivery is the sector of delivering items from a facility to its destination, such as a household. A lot of these companies that are involved in last mile delivery are known as Amazon, Postal Service, FedEx. The last mile delivery sector is one that's very expensive. Currently, as of right now, the cost of each package to deliver is about $1.60. This, of course, varies by weight and things of that nature. The use, however, of using a delivery with autonomous robots is around 6 cents. On the right, we see the figure of the constant growth in using autonomous robots in the delivery market with a 17% compound annual growth rate. So this goes in line to our project scope. We plan to design a fully autonomous delivery robot that can navigate through Cal State LA campus. We are going to do this by using a real-world simulation to demonstrate not only the robot, but its capability. And this, of course, is due to the recent COVID-19 pandemic. And we thought that the project would be much safer to simulate as opposed to building a real prototype. However, we choose to, we plan to provide the same things we would if we were making the actual prototype, such as the physics, mechanics, and the engineering involved overall. Both the robot and the environment will be developed through this simulation and basically envision its autonomous delivery capabilities. The deliverables will be to simulate a four-wheel robotic vehicle capable of the autonomous delivery. It will also, the capabilities involved in autonomy are the obstacle avoidance, navigation, and the computer vision. We also plan to create an environment that resembles Cal State LA, more specifically the student union path that will be mentioned later in the PowerPoint presentation. All these measures are derived from our safety standards, and that is the most important deliverable we plan to bring for our stakeholders that include Cal State LA students as well as faculty and staff. Now we'll go into some of the project structure components. Here's a list of our requirements that is derived from a much larger document. This is a very selected few. We chose these because they involved a lot of the key components in our project. The first one is speed control. As you can see, one of our main focuses is to have the robot only travel at walking speed. This is very important because when you have a robot in a very cluttered environment, such as Cal State LA, we don't want any difficulties happening or any accidents to occur, especially jeopardizing those that come in its path. In the next section, we have the obstacle avoidance program. The first one being the max closing distance to an obstacle being 1 meter. We will be able to see what this is demonstrating wise later on in the project as well. And lastly, the autonomy portion is basically showing some of the key things that our robot will be able to do and is required to do in order to be a fully autonomous delivery robot.
Hello, my name is Ivan Dolores Salazar. Here we will have the team's progress throughout the 2020 to 2021 academic year. The fall semester was mainly used to conduct research. We decided to use Ubuntu 18.04 and ROS to develop the delivery robot based on the compatibility with the hardware. Every team member was assigned a task and they were completed throughout the year. Winter break was also used to conduct research and to further learn how to navigate through ROS. Most of the team's progress was completed towards the end of the spring semester, since it did take a long time to figure out how to implement each task using ROS. Here we have the work breakdown structure. It was divided into 5 sections. The first section is the navigation, and here we have the mechanical lead, Jaime Gonzalez, and he was in charge of the SolidWorks, the Gazebo, the RViz, the SLAM, and the navigation stack. Next, we have the PCB design and electrical lead, Orville Bahia. He was in charge of the electrical design using CAD, Simulink, and PCB. The third section is computer vision. Here we have Francisco Tiquiram. He was in charge of the research, software development, and OpenCV while using the simulation. Fourth section, we have the robot description of the robot by Irvin Martinez. To accomplish this, he used Gazebo, the sensors in Gazebo, subscribers, and publishers. Finally, me, Ivan Dolores Salazar, in charge of the control section. This was accomplished using Gazebo, motion planning, the visual data, and obstacle avoidance program.
Hello everyone, this is Orville Bahia. I will be telling you about the approach of the project. For the system, because of the compatibility, we choose ROS because it is compatible with Ubuntu, and Ubuntu is runs with the Raspberry Pi. These are the electrical components. We will be using a Raspberry Pi for our computer, onboard computer. We are going to be using an array of sensors, starting with the Slamtech lidar. We will also going to use 3 Grove ultrasonic sensors. We will be using a Berry GPS IMU and GPS combination in one module, and then our Ardocam night vision. We will be using 2 DC worm gear type motors and 2 lithium polymer battery packs. This is the electrical block diagram. This shows how everything will be connected together. Starting from the upper left, we will be connecting 2 batteries in parallel, and going to the next one will be the switching circuit module. We are supposed to step down the voltage from 14.8 to 3.3 and 5 volts. The 3.3 rail will power mostly our sensors, including the GPS, the IMU, and the 3 ultrasonic sensors. For the 5 volt, Raspberry Pi is the only one that's going to be connected to that. It's the Ardocam night vision and Slamtech lidar that will be connected directly to Raspberry Pi, including the odometer. To control our 2 DC motors, we have 2 motor controllers that will be connected directly to the battery pack, and it doesn't need step-down voltage. This is the step-down converter schematic I designed using CAD. The top part is the schematic for the 3.3 volts, and the bottom part is for the 5 volts. Using the same software, CAD, I was able to model the step-down converter into a 3D. This is the PCB that can be made out of the Gerber files from that. This can be sent to the manufacturer for them to make it. The left side is the front side, and the right picture shows the rear side of the PCB board. The ports on the front side will have two separate ports for battery inputs on the left side and two separate ports for the motor controllers. On the right side is just the outputs for the 3.3 and 5 volts. Showing again the electrical block diagram, I want us to focus again on the switching circuit module highlighted in the green box. I wanted to simulate the converter in MATLAB Simulink to make sure that our capacitors, inductor, and everything, the diodes work with the value that we decided. I've used some PID controllers to make sure that we have a feedback whenever the load varies, because all throughout the operation of the robot, there's gonna be load and voltage variation, especially when it's going up or down or it's got less load. There are voltage displays on the right, which shows the output of the simulated PCB converter. I've done the power analysis as well. Showing on the right in orange boxes are the sensors and the equipment that's going to be used by the robot. I looked at the data sheets and put in the maximum amperage consumption that it's going to use. Looking at the blue boxes on the left is the rail voltages. We have the 3.3, 5 volt, and 14.8. And this is how everything is going to get connected together. I've added all the current consumptions for each rails and calculated the total power consumed for each. I've also accounted for the power loss through conversion, because our 3.3 volt regulator is 88% efficient, while our 5% is only 77%. Accounting for when the robot is moving at a steady pace of walking speed, which is 3.3 miles per hour, and its total weight, I have come up that it will consume 5 watts. Adding the rest of the sensors and the power loss through conversion, it comes out to sustained power of 13.8 watts, highlighted in green.
Hello, my name is Irvin Martinez, and I will begin discussing the designing process for the delivery robot. Here we have a CAD design of the delivery robot using SolidWorks. The figure shown is a breakdown of the delivery robot into its main components. These include the chassis, where the Arduino camera and radars are located, along with an electronics component, which houses the microcontroller, sensors, and battery source. We also have the motors, wheels, and the top, which houses the lidar and another camera. Here we have a breakdown of the designing process, complete with the features and programs used for the creation of the delivery robot. As you can see, ROS served as backbone for this project, with ROS libraries, commands, and packages used in important steps of the designing process, such as the robot's control, localization, and navigation features. In addition, ROS simulation programs were also used in the testing phase of the robot's functionality. ROS requires a series of files with information describing the delivery robot's physical appearance. These files are known as URDF, short for Universal Robot Description File. URDF files are written in XML format, and is a recommended format as it is both supported by ROS and compatible with the simulator used for this project. In the URDF files, certain parameters are set, such as the color, the shape and position of a component, and the kinematic and collision properties. Ross then uses this information to create a visualization of what the component would look like in real life. The delivery robot design is dependent on two particular parameters, links and joints. Links are used to define a specific component, and it's the first thing that Ross looks for when building the visualization. There are two forms of links, parent and child links. The parent link for the delivery robot is referred to as base link, but in reality, it's the center of the robot's bottom plate. Parent links are defined as the foundation of the overall robot design, while child links are defined as the other components that make up the delivery robot. Child links use the parent link as a reference and are connected together using a joint. For example, after specifying the design parameters for a component such as the chassis, a joint is applied in the URDF specifically for the chassis and the plate. The inclusion of this joint in the URDF allows Ross to generate a visualization where the chassis is attached to the delivery robot's bottom plate. Gazebo was a 3D simulator used for this project. The team selected Gazebo since it is supported by Ross and is compatible with URDF. One important feature that Gazebo has is the Open Dynamics Engine, or ODE, which is a physics engine complete with collision detection features. Therefore, any environment created in Gazebo would allow the delivery robot to behave in a manner similar to how it would in the real world. For instance, if the delivery robot were to make contact with an object, the robot would collide with the object rather than simply go through it. One of the environments that the team used is loosely based on the location around Cal State LA, where the Student Union building is. In this environment, the team included models of things that the delivery robot may encounter in real life, such as people, cars, and tables.
I will now begin explaining the control mechanism of the robot. We began the process of manually controlling the delivery robot using a teleoperator. The teleoperator uses the keyboard of a computer to drive the robot manually. The keys that are used from the computer keyboard are I, J, K, L, and comma. The figure on the bottom right shows the different keys and their commands. I will be used to make the robot move forward, comma will make the robot move backwards, J will make the robot turn left in place, L will make the robot turn right in place, and finally K and any other key on the keyboard will stop the robot from moving. Now, the obstacle avoidance program was designed using Python and a lidar. The code can be changed to address the bugs that may occur in the simulation, such as finding the maximum gap between the robot and the obstacle. The obstacle avoidance program begins by the lidar reading the distance. If the distance between the robot and the object is less than 1 meter, then the robot will start rotating until that gap is greater than 1 meter. After this is done, then the robot will continue moving forward. However, if this conditional statement is false, then the lidar will continue reading the distance between the object and the robot itself, and the robot will continue moving forward. Here, we will exhibit the obstacle avoidance program. The purpose of this demo is to demonstrate the obstacle avoidance capabilities of the delivery robot. The robot will avoid any obstacle that is within a meter gap. The speed of the robot is set to 1 meters per second. However, this video has been sped up to 8 times since the simulation runs at a slow speed. With the use of the camera attached onto the robot, we can view the Gazebo simulated world in the robot's point of view. As we can see, the robot will navigate through the campus, at the same time avoiding any obstacle it comes in front of. Here we have students showcasing the robots such as the Mars rover on the left and the Turtle bot on your left again. As you can see, our obstacle avoidance program has successfully avoided any obstacles it comes in contact with.
Hello, everyone. So now we will go into the RViz and localization portion of this project. We have successfully completed the obstacle avoidance program. Now we can begin to run a more sophisticated program within navigation. First, we begin with RViz, which is ROS visualization. Aside from Gazebo, which is another visual simulation, RViz helps us to visualize the sensors that are within the robot. As you can see here in the figure on the right, we can see the obstacles that are being indicated by the red lines. So on top of the lidar sensor, we can also visualize what the camera is seeing, as well as the odometry of the robot, which we'll get into. In this portion for the localization, we use G-mapping SLAM. This is known as SLAM G-mapping. G-mapping is a pre-installed package in ROS, which is an algorithm for localization. Localization is the process for establishing a character or an entity to the map, or a particular place that something is in. So in this case, we are using localization in the process of establishing the robot to the student union path, so we can create an internal map. And we're doing that by using the G-mapping package and the lidar sensor that is on the robot. So in this portion here, on the figure on the right, we can see that the robot is already establishing areas where the obstacles are not found. Therefore, we can use our obstacle avoidance program to run randomly throughout this map, and we can create that internal map, which will help us in the next section of the project in navigation. Here we have a network of the navigation nodes we will be using for this portion of the project. So a node is basically something that ROS uses that incorporates a publisher or a subscriber, or sometimes both. A publisher sends data to a topic or sends data to a command, whereas a subscriber receives data or receives topic information and uses that data. So we begin on the left, highlighted is Gazebo. Gazebo itself is the simulation, and this incorporates all the physics and the engines that we need to simulate our project. Next, we have the robot state publisher. So like I said, the robot state publisher will acquire the robot state, which it will subscribe from the Gazebo, and it will then publish that to the robot visualization, so we can visualize some of the things that we can't see on Gazebo, such as the sensors and the lidars, the lidar and the odometry. So that's the portion where RViz will assist us. Next here we have AMCL highlighted. What AMCL is, it actually incorporates the localization and the odometry, as we can see here from the arrows. And it helps us to develop a local and a global path. And what that is a local path is the immediate path the robot is taking within the internal map. The global path is the overall path the robot will take throughout the map. So as of right now, we are trying to establish a path where if the robot is given a specific navigation goal, the robot will be able to independently develop that efficient path that avoids the obstacles to get to that point. So that's where that process of localization helped us, because again, localization helped us to, using G-mapping, develop what we have here is the map server, which is highlighted now, and that is the internal map for this node network. All these three nodes will be moving into the move base node, and what this is it's using all the information from the localization internal map and the development of the local and global paths from AMCL. And this is gonna then, it subscribes that information, and then it will publish the information to a topic known as velocity controller. So you'll be able to see that at the bottom of the network. That is the main purpose of move base, is to publish a velocity command to the controller of the robot. And this will happen repeatedly because the controller will then go to Gazebo, where the robot is actually being simulated and the controller is actually controlling the robot for the user to see. Here we're going to have a test run of the technology and the software we were able to establish with our robot. The student union path is being presented here in Gazebo. We have the initial position of the robot, and we have a navigation goal, which is a group of students here enjoying a nice lunch meal. So the robot has been given that task. It's been given that navigation goal through RViz, and we'll see that in a minute what that looks like. Here, this is what Gazebo, which you will be able to see in simulation, and pretty much what you would be able to see in real life. Once we transition in a bit to the RViz here, we will be able to see internally what the robot is seeing using its hardware. So here, the green line is indicated by the local planner, and the inaccessible areas are not highlighted, or they are blank with empty voids. And this is pretty much the path that the robot cannot go into. So a lot of the white areas the robot will be able to traverse to, and its hardware will be able to detect, I can take a path in those areas there. And this is all done independently by the robot, not by the user. So as we go more, we see that the blue line is the global path, which is the overall path of the robot. And lastly, the red lines again are just what the lidar is detecting from the robot's lidar sensor. So as we round about to the final destination of the robot, as we can see, it independently went and took this path. It avoided all obstacles using a combination of our localization, obstacle avoidance program, and the AMCL node. So again, all these together create the navigation node network that we were looking for when developing this project.
Hello, my name is Francisco Tiquiram, and I'll introduce you guys to computer vision. Computer vision is a form of teaching a computer or robot how to identify images and video from a camera, such as a webcam. Companies such as Postmates, DoorDash, Amazon, and many others are researching and applying this form of technology to help humanity, especially in this pandemic. For the project, we used Linux as our operating system, meaning Ubuntu, Python as the programming language, OpenCV as a computer vision library, and Notepad++ as the code editor. Now let's explain the most basics for computer vision. Here we have a diagram that represents the way we will apply it to the project. The programming language imports OpenCV to communicate to our camera. We do that by using an object that's called cv2.video capture, which captures video from a webcam, and from there we can add desired operations, as we will demonstrate in the following demos. And as we can see from the image to our right, we have some toy cars and a phone, and that's what has been captured from cv2.video capture. And we could determine that the camera is the visual aid for the robot as we implement it in the future. Here's one of the first demos. So the demo shows how to manually apply a threshold to an object by isolating its surrounding. This is important to the robot, for example, to find its docking station when the battery is low. And as you can see from the video, I am manually moving the sliders to isolate the little orange car. And from the pictures to the right, which was taken as a separate demo, here we're trying to isolate the car from the post-it. And like stated before, this could be very useful for the robot. In the next demo, we apply threshold too, but we also add contours to outline objects to determine a shape of an object. Also, we want to use a grayscale because it uses less complexity. And when we think of data, color adds an additional amount of storage. This demo is a brief introduction to computer vision to also determine the area of an object. It is manually set. As we can see, it is trying to detect the area of the box. And like stated before, it is important to isolate items, undesired items or objects, and the robot's surroundings will just be more complex for the robot to detect and determine. These demos are just um, set manually. They're not autonomous, but as we move forward, we hope to add autonomous to the robot. For future implementations, it is of great importance to add more complexity to the robot as seen in the diagram. For example, adding machine learning can help the robot learn and determine what object is detecting by gathering the data, especially machine learning. Machine learning we could use, for example, TensorFlow Lite in the Raspberry Pi, and which could help in determining certain objects, not by teaching it, but by automatically knowing with the data already gathered, which is important for the robot because the robot needs training. And adding more complexity can be used for better decision making as they traverse around their environment.
Here we will go over the results of the project. Overall, the results we have seen in the design process for the simulation that has been presented already, along with our computer vision. Here's a table basically going over much of the stuff in the presentation. The hardware portion is just the simulated portion or the design portion. Of course, we didn't use any actual hardware components due to the pandemic. However, we feel that some of the stuff that we simulated or designed through SolidWorks and through the electrical components and MATLAB as well, will be able to assist any future team that is actually able to implement the coding and software to actual hardware and components. We'll go down to the software portion where we're basically relating some of these tasks completed to what are requirements of the robot. As we go to near the bottom where we're using the navigation, the computer vision, and the autonomy overall, we didn't give ourselves the full completion because we feel that we didn't exactly implement all of these components how we would like, or I guess how it would be in an actual prototype for a robot in CalCLA. However, for being in the first year, I believe we took a large step in completing a lot of the requirements and deliverables, and any future iterations of the project will have a good head start from this point on right here.
Okay. Due to the time constraints in the COVID-19 pandemic, the risk assessment for this project was mostly software and design based. The evaluated risks are a combination of risks that were encountered during simulation testing, as well as risks the robot could face in the real world. The team used a 1 to 5 level scale to evaluate both the likelihood of the risk presenting itself, as well as the impact that the risk may have. A level 1 risk would indicate a risk that is rarely bound to happen, with an impact that will not affect the delivery robot's function or ability to carry out its tasks. On the other hand, a level 5 risk would suggest a risk that is expected to happen, with an impact that would be considered catastrophic and potentially render the robot useless.
I will now dive into the conclusion. To summarize, RViz was our best option to ensure the safety and health of our team, given the unforeseen circumstances. With a combination of sensors, the control system, navigation, localization, and computer vision, a fully autonomous delivery robot is accomplished. Delivery robots are essential for business and are a perfect solution for delivery services during a pandemic. Thank you for your attention. And this concludes our presentation.